Now that we have all these concentration units, we want to talk about converting between them. So we have our 4 types of concentration units: molarity, molality, mole fraction, percent composition. And all of them are looking to do functionally the same thing. How much solute per amount of solution? Give an idea of how much stuff is dissolved in your solution. And so the reason why we have all these different methods or different kind of ways to describe functionally the same thing is because they have different applications. Molarity is a very chemical unit that's used a lot in stoichiometry because it's moles per liter. And you need moles, that's number of molecules per amount of solution. So then you can just measure out an amount of solution to get the right amount of, say, solute to do a reaction with. Molality is this very artificial moles of solute per mass of solvent. It's really only used for colligative property applications, explicitly boiling point elevation and freezing point depression, because temperature is changing and molality doesn't change when temperature changes. It also has that solvent that's weird on the bottom. Molality was invented for colligative properties. Mole fraction is actually one of the more generic ones, and mole fraction, its utility is limited in that it's unitless, but it is useful. It has the kind of widest range of applications, and that you can characterize as many different things that are mixed together, and you can characterize the solvent. So when you start to make more complicated mixtures, when you have, say, 3, 4, 5, 6, 7 things mixed together, you have to use mole fraction because it stops being clear what the solvent is. When the most you have is like, say, 15% of any one thing. So you use mole fraction to kind of describe it. It's also a very chemical description because it's all about the number of molecules, right? What you have on a molecular count basis. And then percent composition is the most common everyday one that's used. And you'll note the reason is because it's mass over mass. All of the other ones have either moles explicitly in them or particular types of units, liters or kilograms. Percent composition lets you just use the units you calculated your amount in. So percent composition is generally really useful when it's just like, I want to mix, say I'm going to dissolve some bleach in water. I just measure out an amount and it's 5% of the total, boom, it's just 5, right? And so that's why percent composition is really common, say in grocery stores or even in a pharmaceutical setting, because you just describe the composition based off how you measured out the components. It's not necessarily the most useful chemically, but it is the easiest to use. So these all have the same idea of, we just use them in different kind of iterations. So the thing is, all of these concentration units always have the same general form. Amount of solute, usually over amount of solution. There's some variability on the bottom there. And so they all have the same general form, which means if you are describing a particular solution using one of those units, you can also use any other concentration to describe that same solution, because they all have the same relative types of information, amount of solute per amount of solution. So there's going to be an overall process that we can go through to work through this. Instead of me just talking about it, we're going to work through an example first and then kind of touch base on how to work through those. It's going to work better if we just kind of I'll walk through the process, and then we'll kind of talk about it and review some of what we did there on the other side of it. The mass percent of NaCl in seawater is 3.5%. If the density of seawater is 1.03 grams per milliliter, what is the molarity of NaCl in seawater? So this would be an example. That mass percent is actually relatively straightforward to obtain for salt in seawater. You just boil away all the seawater and measure the mass of the salt that's left versus the mass you started with. And so you can figure out those mass percents relatively experimentally. It's not that difficult. That's the numbers you would get from the experiment. But we may care about the molarity because we're chemists. We want to know relative to, say, other molar concentrations or how we could prepare this in the lab. All right, so we got the mass percent of NaCl in seawater as 3.5%, and I want to know the molarity. And so when we want the molarity, that's a concentration unit. We have a different concentration unit, a different concentration description. And so this is where we need to be doing a concentration conversion. So normally when we think about doing a conversion, right, we'd have like 3.5%, divide out the percent concentration, multiply in the molarity. But when you're doing conversions with concentration units, it's not going to work quite so cleanly. Instead, we're going to do a slightly different approach. So if we take this 3.5%, we know that if we have mass percent, we know that that is mass of solute divided by mass of solution times 100. And what we want to get is molarity. And so we know that molarity is equal to moles of solute divided by liters of solution. And so how I'm going to approach this conversion is what I'm going to say is instead of trying to go from percent concentration straight into molarity, I'm going to take an amount of solute and turn that into a different amount of solute. I'm going to take an amount of solution and turn that into a different amount of solution. And so we can see here, if we just break it up, this is mass of solute to moles of solute. That can be accomplished using a molar mass conversion. That's the kind of conversion we have experience with. Down here, I have mass of solution into the volume of solution in liters. Again, it's the same it's the same matter you're talking about, the solution. What you're changing is whether or not it's described in mass or in volume as liters. And so we're going to break it up into those two parts. So in order to do that, we need a value here. So when we're doing a concentration conversion, our first step is going to be coming up with values. So values for my initial concentration. And when I say values, what I mean is masses, a mass of solute and a mass of solution in this case. So I know that overall my concentration is 3.5%. And that mass, that comes from a mass of solute and particular mass of solution for my given sample. And so I can put values in here for any, there's a lot of different combinations that give me 3.5. But what I'm going to say is, well, suppose I have 3.5 grams of solute, so NaCl, divided by 100 grams of solution. And then there is the times 100. And so if I look at that, I have, if I do 3.5 divided by 100 times 100, those 100s are going to cancel out, and the answer would be 3.5%. So you can choose any value. We could have put like 60 up here, and then we could have done some algebra to figure out what the bottom number is. But we need two numbers. We might as well pick numbers that make our lives as easy as possible. If I put 100 grams down here, the number up top is just the same as that because the 100s cancel out. So these are the like initial values that I can just suppose I've just said is 3.5%. Well, let's suppose I've gotten a sample of seawater that is 100 grams. And that means if it is 100 grams of seawater, it's going to contain 3.5 grams of NaCl. So I'm just going to assume that that's the case, and I'm going to work from there. Because now what that lets me do is break it up into, I can do the convert the solute, which is really the numerator part. And so in this case, I can see I have 3.5 grams of NaCl. What I want is to be in moles, so I can use the molar mass. (58.44 grams of NaCl for every 1 mole of NaCl means that in this I have 0.060 moles of NaCl. So perfect. That was the top conversion that I needed. I want a molarity. If I have a moles of solute and a liters of solution, I'll be good to go. So I converted that out. I also need to convert, in this case, the solution, which is the denominator of my fractions. And so I started with 100 grams of seawater. That's the name of my solution. And I want it in volume. I want it in liters. So the first thing is going to be, I need to go from mass into volume. And that is where the density is going to come in. Just like we used the molar mass on the last one to go from mass to moles, that's a common conversion factor in the world of doing this concentration conversions. We also use the density quite a bit because there's a lot of masses and volumes that show up in the denominators especially. And so I can use my density, which is 1.03 grams per 1 milliliter, and that is still for seawater. That's for the solution overall. You will know you want to be careful if you're dealing with the mass of the solution. It needs to be the density of the solution. The density of seawater is slightly different than the density of pure water. I get I get 97 milliliters. So I'm from mass into volume, which is good. That's what the density allows me to do. Now I need to get all the way to liters. So I'm in 97 milliliters. I need to go the rest of the way into liters. There are 1,000 milliliters in a liter, 0.097 liters. So my 100 grams of seawater is the same as calling it 0.097 liters of seawater. Oh, I should label that. And so the final step I got the components. I got my new numerator and denominator. Well, I want to put them together. Molarity in this case is going to be moles of NaCl for liters of seawater. I calculated those out. Oh, next page, this is molarity of the NaCl. So when we have one representation of concentration and we want a different unit, the process is always going to be the same idea. It's very, very difficult to go directly, just like one multiplication division from, say, percent or any concentration directly to another. But we can always always have that ratio form. Concentrations are always in ratio form, and we can do the top part and the bottom part, and just do those in two parts, and then recombine them into our new equation for whatever it is. Because we are converting our concentrations, we're doing that top part of the fraction, and then we're doing the bottom part of the fraction, right? We're converting the numerator and the denominator separately, the amount of solute and the amount of solution separately. So when we are given our initial concentration, we always want to take that and turn it into an explicit ratio. So that describes that concentration can describe any number of solutions. But what you can do is choose your ratio that it makes your life easy. And basically what you do is you choose the denominator amount to just be whatever the baseline is. So say for molarity, say 3.4 molar, that would be 3.4 moles of whatever your solute is per 1 liter of solution. And so the numbers you can use are just 3.4 moles and 1 liter and convert those out. You could also use 1.7 moles and 0.5 liters. You would still get 3.4, but you would have to do some algebra to figure out those initials. So you could just say, I'm going to do 50 up top. I'm going to do 50 moles, and then you would have to figure out what the liters are. But it'd be some number of liters, and you'd have to do an algebra problem in the front. If you just choose 1 as your liter, the top number, the numerator, is just equal to whatever the molarity was. Same idea for mole fraction. You use 1 total mole. Same idea for molarity. You use 1 kilogram. Percentage is a little bit different because it's based out of 100 because it's a percent, but you just use 100 there, right? So it's not, you don't use the 1, but you use the 100. And so that's just an idea of you need to always, if you're doing a conversion of concentration, you need to break it up into 2 parts. You need to break it up into the solute, that numerator part, and the solution, the denominator part. There is, of course, one exception, and that is the solvent on molarity. You will note that that is different. Everything else is solution total mole, which is still the same thing as the solution, and solution, right? So those are all describing both the solute and solvent together, but molality is not. That is only solvent. So when you're dealing with molality, it's going to be a little bit different. You can't use a multiplication conversion. You need to use addition. So those concentration, those conversions, once you break it up into the solute, the numerator part, and the solution, the bottom part, common conversions are density, which lets you do mass to volume. For pure substances, you can look those up. So say for water is 1 gram per milliliter. But if it's a solution, like salt water does not have the same density as pure water. There's additional mass in there, and you would need to be given that. So a lot of times, like we saw in the example, that was just given in the prompt. Molar mass is something you can always calculate. Mass to moles, we've seen throughout all this concentration stuff, very common conversion, those molar masses. And then the other thing I want to point out is these equations for going between solution and solvent. You have to do this whenever you're going in or out of molality, because this denominator in molality is only solvent. It's only solvent here. And so that only works, solvent mass. If you want to convert that into solution mass, you need to add in the solute to that solvent. So you need to use some addition to go back and forth. So we want to be mindful of that. You may also have to do a conversion of that mass afterwards. You can also do it in total moles if you wanted. Addition works there, but you cannot do addition in volume. It's not additive. So if you add 20 milliliters of ethanol and you dissolve it into 60 milliliters of water, the resulting solution does not, the volume of the resulting solution is not the sum of those. Basically, the molecules end up getting either packing closer together or further apart. So the volume does not add. Mass and moles add, volume does not. Participation 127, question 3. The mass percent of NaCl in seawater is 3.5%. What is the molality of NaCl in seawater? Molar mass of water is 18.02 grams per mole. Sodium chloride is 58.44 grams per mole. This is the third question on participation 127 due Tuesday, January 27th at 11:59 p.m. The link to the assignment is right below the document where there are the links to these videos. Again, the mass percent of NaCl in seawater is 3.5%. What is the molality of NaCl in seawater? Molar masses for water and sodium chloride are both given. All right, one more video left. Looking for any more questions on participation 127. And we're coming up, this is the end of chapter 11. I'll see you in the next video. Bye-bye.